Hey, you all. Did you know that right now, yes, as you're listening to this, there are particles in your body, in the air around you, even in the screen you're watching on, that are not in just one place, but in two places at once. And not just two, sometimes three, 10, or even an infinite number of places, all at the same time. Sounds impossible, doesn't it? Because in our everyday world, things are where they are. Your coffee cup is on the table, not also on the floor or in the fridge or halfway to the moon. But down at the level of electrons, photons, atoms, even molecules under the right conditions, the rules change completely. This isn't science fiction. It's not speculation. It's been tested, verified, and used to build real technologies, like the lasers in your DVD player, the transistors in your phone, and the ultra-precise clocks that keep GPS working. What we're talking about is one of the most fundamental ideas in all of modern physics: quantum superposition. So what exactly is quantum superposition? In the simplest terms, it's the ability of a quantum system, like an electron or a photon, to exist in multiple states or locations simultaneously, until something forces it to choose just one. Think of it like this. If you flipped a coin in the dark and didn't look at it, in our everyday world, the coin is either heads or tails. You just don't know which yet. But in the quantum world, before you look, the coin is genuinely both heads and tails at the same time. It's not that we lack information. It's that reality itself hasn't settled on a definite outcome. And this isn't just philosophical wordplay. It's built into the mathematics of quantum mechanics. And more importantly, it's built into how the universe behaves. Today, we're going to explore this idea step by step. We'll start with why classical physics, Newton's world, breaks down at tiny scales. Then we'll meet the key experiments that forced physicists to accept the strange reality of superposition. We'll unpack the meaning of the wave function, the central object in quantum theory, and explain how it encodes probabilities, interference, and multiple possibilities in one mathematical description. We'll see how superposition leads to interference patterns that can't be explained any other way. Then, we'll talk about what happens when we measure a quantum system, how looking forces it to pick a state, and why that's so deeply puzzling. Finally, we'll touch on real-world applications, like quantum computing and quantum cryptography, where superposition isn't just weird, it's useful. And don't worry, we won't be throwing equations at you with Greek letters and squiggles. Every formula will be spoken out fully in words. Our goal isn't to do calculations, it's to understand what's happening in plain language so the ideas stick, even if you're half asleep. Because the truth is, this stuff is strange, but it's also beautifully logical once you see the pattern. So let's begin back at the beginning. For over 200 years, from the late 1600s to the early 1900s, physics was ruled by the laws Isaac Newton gave us. Newton told us how objects move when forces act on them. He gave us a formula: acceleration equals force divided by mass. In words, the acceleration of an object is equal to the net force acting on that object, divided by its inertial mass. That means if you push something harder, it speeds up faster. If it's more massive, it resists acceleration more. Simple, powerful, and for planets, baseballs, bridges, and cars, it works perfectly. Newton also believed that if you knew the position and velocity of every particle in the universe at one moment, and you knew all the forces, you could, in principle, predict the entire future and retrodict the entire past with perfect accuracy. That idea, called determinism, was the bedrock of classical physics. The universe was like a clockwork machine. Set the gears in motion, and everything unfolds inevitably. But then at the end of the 1800s, cracks started to appear. Scientists studying light and heat found things Newton's laws couldn't explain. For example, when you heat up a piece of metal, it glows, first dull red, then orange, yellow, white. Physicists tried to calculate how much light of each color should be emitted, using classical physics, and their prediction exploded to infinity at short wavelengths. They called it the ultraviolet catastrophe because it predicted infinite energy in the ultraviolet part of the spectrum, which obviously doesn't happen. Reality glows nicely. Theory screamed nonsense. Enter Max Planck in 1900. He proposed a radical fix. Maybe energy isn't continuous. Maybe it comes in little chunks, packets that he called quanta. The energy of each packet equals a constant, which we now call Planck's constant, multiplied by the frequency of the light. In words, energy equals Planck's constant times frequency. That simple idea fixed the math and matched the experiments perfectly. Light, it seemed, was acting like it was made of particles, even though everything else said light was a wave. Then came Albert Einstein in 1905. The same year he published his theory of special relativity. Einstein took Planck's idea seriously. He said, maybe light really is made of particles, later called photons, and each one carries a quantum of energy. He used this to explain the photoelectric effect. When you shine light on certain metals, electrons pop out. But here's the weird part. Classical physics said brighter light, more intensity, should knock out electrons with more energy. But experiments showed that wasn't true. Instead, it was the color, the frequency of the light that mattered. Red light, no matter how bright, wouldn't eject electrons at all. But even dim blue light would, and the electrons came out with higher energy. Einstein explained it by saying, each electron is knocked out by a single photon. If the photon doesn't have enough energy, which depends only on its frequency, not its brightness, it can't free the electron. So the energy of the ejected electron equals the energy of the incoming photon, minus the binding energy that held the electron in the metal. In words, electron energy equals Planck's constant times frequency, minus the work function of the material. This was huge. Light, which for a century had been proven to be a wave, interfering, diffracting, bending around corners, was now also acting like a stream of particles. Wave-particle duality had entered the stage. But the real shock came a few years later from a completely different direction. In 1924, a French graduate student named Louis de Broglie made a stunning proposal. If light, traditionally a wave, can behave like particles, then maybe particles, like electrons, can behave like waves. He said, every particle has a wavelength associated with it. That wavelength equals Planck's constant, divided by the momentum of the particle. In words, wavelength equals Planck's constant divided by mass times velocity. So the heavier or faster the particle, the shorter the wavelength. For a baseball, it's unimaginably tiny, way smaller than an atom, so we never notice it. But for an electron, very light, moving at modest speeds, the wavelength is about the size of an atom. That means electrons should diffract and interfere, just like light waves. And in 1927, two experiments confirmed it, almost simultaneously. Clinton Davison and Lester Germer in the United States, and George Paget Thomson in England, both fired beams of electrons at crystals. Crystals act like natural diffraction gratings for waves, with regularly spaced atoms that scatter waves in specific directions. And sure enough, they saw interference patterns. Bright and dark rings, exactly what you'd get if electrons were waves interfering with themselves. Not random scattering, not particle-like impacts, clear, wave-like interference. That meant electrons weren't just little billiard balls. They had wave nature. So what is waving? That's where Erwin Schrödinger comes in 1926. He proposed a wave equation, a formula that describes how this quantum wave evolves over time. The central object is called the wave function. We usually denote it with the Greek letter psi, but again, we'll avoid symbols. Let's call it the quantum state wave. This wave doesn't represent a physical wave, like water or sound. It's a mathematical function that contains all the information we can possibly know about a quantum system. And crucially, the square of the amplitude of this wave, at any point in space, gives the probability of finding the particle there if we look. In words, The probability of detecting the particle at a given location is proportional to the square of the height of the quantum state wave at that location. That's a big shift. In classical physics, waves carry energy. In quantum physics, the wave carries information, specifically probabilistic information. And here, where superposition enters formally. Schrödinger's equation has a special property: it's linear. That means if you have two possible solutions, say one wave that describes the particle going through the left slit in an experiment, and another wave that describes it going through the right slit, then the sum of those two waves is also a valid solution. In other words, the particle can be in a state that is a combination, or superposition, of left slit and right slit at the same time. Let me stress this. It's not that the particle goes through one slit or the other and we don't know which. It's that the quantum state is genuinely a blend of both possibilities. And this isn't metaphorical, because when you add the two waves, they interfere like ripples on a pond. Where peaks meet peaks, they reinforce, high probability. Where peak meets trough, they cancel, zero probability. That interference shows up in the pattern of where particles land on a detector screen. And if the particle had gone through only one slit, you just get a single blob behind each slit. But with two slits open and no measurement, you get stripes, bright and dark bands, exactly matching wave interference. This is the famous double-slit experiment, and it's the heart of quantum weirdness. Let's walk through it slowly. Imagine a barrier with two narrow, closely spaced slits. Behind it, a screen that lights up where particles hit, like a phosphor screen. First, fire tiny classical particles, say sand grains, through the slits. Each grain goes through one slit or the other and hits the screen behind that slit. After many grains, you get two clusters, one behind each slit. Now do the same with water waves. A wave hits the barrier, it spreads out through both slits. Each slit becomes a new source of circular waves. Those waves overlap on the other side. Where crest meets crest, you get a bigger wave, constructive interference. Where crest meets trough, they cancel, destructive interference. On the screen, you'd see a pattern of alternating high and low intensity, stripes. Now electrons, fire them one at a time. Not a beam, one electron, wait, then another, so they can't interact with each other. What do you see? At first, each electron makes a single dot on the screen like a particle. But after hundreds or thousands, the dots build up into an interference pattern, stripes, just like the water wave. That means each electron by itself must have gone through both slits and interfered with itself. Because if it only went through one, how could it know whether the other slit was open or closed? And indeed, if you close one slit, the interference pattern disappears. You get just one blob. Open both, stripes come back. But here's the kicker. If you try to detect which slit the electron goes through, put a little sensor at each slit to watch. The interference pattern vanishes. You get two blobs again, just like classical particles. The very act of measuring, of asking which path, destroys the superposition. The electron is forced to behave like it went through one slit or the other. So what's happening? The quantum state, the wave function, starts out spread out. It evolves through both slits. The parts from each slit overlap and interfere. The probability of where the electron lands is governed by that interference. But when you make a measurement, when the electron interacts with a macroscopic detector, the wave function appears to collapse. It jumps from being spread out to being sharply peaked at one location. Now important, no one actually sees the collapse happen. It's not a physical process we can watch in slow motion. It's a description of what we observe. Before measurement, multiple possibilities coexist. After, only one is realized. And which one? Random, but weighted by the probabilities given by the wave function. So superposition isn't just we don't know. It's all options are physically present in the description, and they influence each other. Interference is the smoking gun, because interference requires two things to be happening at once. You can't interfere with nothing. Let's make this concrete with a simpler system, the quantum bit or qubit. In classical computing, a bit is either 0 or 1, a switch off or on, but a qubit can be in a superposition of 0 and 1. Its state is described by two numbers. Let's call them alpha and beta. Alpha tells you how much zeroness it has. Beta tells you how much oneness. But these aren't probabilities yet. The actual probability of measuring 0 is alpha squared. The probability of measuring 1 is beta squared. And crucially, alpha squared plus beta squared must equal 1. That ensures the total probability is 100%. In words, the probability of finding the qubit in state 0 equals the square of the first coefficient. The probability of finding it in state 1 equals the square of the second coefficient. And the sum of these two probabilities equals 1. But here, the magic. While the qubit is in superposition, it's not secretly 0 or 1. It's in a new state, a blend. And because of that, when you manipulate qubits, using lasers, magnetic fields, microwave pulses, you can make the 0 and 1 parts interfere. You can rotate the state, amplify certain outcomes, cancel others. That's how quantum algorithms get their power. They choreograph interference among vast numbers of possibilities, so that wrong answers cancel out and right answers reinforce. But again, measurement ruins it. Look too soon and you collapse the state. So quantum computation has to carefully delay measurement until the very end, after all the interference has done its work. Now let's go back to location. A particle in superposition of two places, say position A and position B, doesn't mean it's halfway between them. It means its wave function has a bump near A and a bump near B. The particle has no definite position until measured. The expectation value, that is, the average position you'd get if you repeated the experiment many times, is somewhere in between, but any single measurement gives you either A or B, or somewhere near them, depending on how spread out the bumps are. How do we create such a superposition? One way is with a beam splitter. Imagine a half-silvered mirror, glass coated so that 50% of light reflects, 50% transmits. Shine a single photon at it. Classically, you'd expect it to either reflect or transmit randomly. But quantum mechanically, the photon enters a superposition. 50% reflected, 50% transmitted. The wave function splits. If you send the two paths to recombine later, say with mirrors, you can get interference again. That's the basis of the Mach-Zehnder interferometer, a key tool in quantum optics. In such a device, you can adjust the path lengths. If the two arms are exactly equal, all photons exit one port due to constructive interference. Lengthen one arm by half a wavelength, and they all exit the other port. Destructive interference in the first. The photon doesn't choose a path, it takes both, and the phases of the two parts determine where it ends up. But again, if you put a detector in one arm to see which way it went, the interference vanishes. You get 50-50 at the outputs. The superposition is destroyed. This leads to what's called the measurement problem, one of the deepest unsolved questions in physics. Why does measurement cause collapse? What counts as a measurement? Is it consciousness? Large systems? Irreversible interactions? There's no consensus. The standard textbook answer is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg. It says, the wave function is a tool for calculating probabilities. It's not real, it's just knowledge. Superposition is a statement about potential outcomes, not actual simultaneous existence. When you measure, you update your knowledge and the wave function jumps. But many physicists find that unsatisfying, because interference proves the wave function has physical consequences. If it were just ignorance, how could two possibilities cancel each other out? Enter Hugh Everett in 1957. He proposed the many worlds interpretation. His idea, there is no collapse. The wave function always evolves smoothly via Schrödinger's equation. When a measurement happens, the observer becomes entangled with the system. So if the electron is in superposition of spin up and spin down and you measure it, you enter a superposition of seeing up and seeing down. But since you're a big, complex system, these two versions of you don't interact. Each thinks they saw a definite result. The universe splits, not physically, but in the mathematical structure of the wave function, into branches. All outcomes happen, just in different, non-communicating parts of reality. In this view, superposition never ends. It just spreads. You're in superposition right now of having heard this sentence and not having heard it, except the not having heard it branch is so vastly suppressed by decoherence that it's effectively gone. Which brings us to decoherence, the modern bridge between quantum and classical. Decoherence explains why we don't see superpositions in everyday life. Here, how it works. No quantum system is ever perfectly isolated. It's always interacting with its environment, air molecules, photons, thermal vibrations. Each interaction entangles the system with the environment. Suppose an electron is in superposition of being here and there. A single photon bounces off it. If the electron is here, the photon scatters one way, if there, another way. Now the photon's state records the position. But we don't track every photon, so we average over all possible photon states. When you do that mathematically, the interference terms, those delicate plus and minus combinations that give superposition its power, get washed out. What's left looks like a classical probability distribution. 50% here, 50% there, but no interference. In words, the loss of quantum coherence due to interaction with the environment causes the system to appear classical, even though the full wave function, including environment, still evolves unitarily. Decoherence happens incredibly fast for large objects. For an electron in vacuum, superposition can last seconds or longer. For a large molecule, milliseconds. For a dust grain, femtoseconds. So big things can in principle be in two places at once, but they decohere so fast we never see it. Still, experiments keep pushing the boundary. In 2010, researchers put a tiny mechanical resonator, a microscopic paddle, into superposition of vibrating and not vibrating. In 2019, a molecule with over 2,000 atoms was put through a double slit and showed interference. So size isn't the limit, it's isolation. Keep it cold, keep it dark, keep it still, and quantumness survives. Let's now talk about energy superposition, because superposition isn't just about location. It can be about any property: spin, polarization, energy level. Take an atom. Electrons orbit in specific energy levels, like rungs on a ladder. They can't have energy in between. To jump up, an electron absorbs a photon with exactly the energy difference between levels. To jump down, it emits one. But what if the atom is exposed to light that's not exactly the right frequency? Classically, nothing happens, but quantum mechanically, the atom can enter a superposition of ground state and excited state. The electron isn't up or down, it's in a blend. And this superposition oscillates. The probability of being excited goes up and down in time, like a pendulum swinging between two states. This is called Rabi oscillation. The frequency of that oscillation depends on the strength of the light and how close its frequency is to the natural transition frequency. In words, the Rabi frequency equals the product of the electric dipole moment of the transition and the amplitude of the electric field, divided by Planck's constant. This is how atomic clocks work. You tune a microwave field to the exact frequency that drives transitions in cesium atoms. When it's perfect, the atoms flip from one state to another with maximum efficiency. That resonance defines the second. 9,192,631,770 cycles of that radiation equals 1 second. But during the flip, the atom is in superposition, and that superposition is coherent. The phase matters, which is why atomic clocks are so precise. They're measuring the phase of a quantum wave. Now let's return to the double slit, but with a twist. Imagine doing the experiment not with electrons, but with entangled particles. Say you generate two photons that are entangled in position. If one goes left, the other goes right, and vice versa. But until measured, both are in superposition. Now send photon A through a double slit. Photon B goes somewhere else, say to a distant lab. If you just look at where it lands, you see no interference, just a blob, because its path is correlated with B. But if you later compare A's position with B's measurement and select only the cases where B was measured in a particular way, you can retrospectively recover interference for A. This is the quantum eraser experiment. It shows that which path information, even if stored far away and never looked at, destroys interference. But if that information is erased by measuring B in a basis that doesn't reveal the path, interference comes back. Crucially, you can't use this to send messages faster than light, because the interference only appears after comparing both results classically. No signal is transmitted, but it does show that quantum correlations are non-local. They link distant events in ways classical physics can't replicate. And that brings us to Bell's theorem, 1964. John Bell proved mathematically that no local hidden variable theory can reproduce all the predictions of quantum mechanics. Hidden variables would be little instructions carried by particles, saying, if measured this way, give this result. Local means they can't communicate faster than light. Bell derived an inequality, a limit on how correlated measurements can be. If reality is local and real, meaning properties exist before measurement. Quantum mechanics predicts violations of this inequality, and experiments, starting with a Lane aspect in the 1980s, confirmed it. Entangled particles are more correlated than any classical mechanism could explain. So superposition isn't just incomplete knowledge, it's fundamental. The universe really does hold multiple possibilities in tension until an interaction resolves them. Now, practical applications. You've probably heard of quantum computing. A classical computer with n bits can be in one of 2 to the power n states at a time, like a single point in a vast space. A quantum computer with n qubits can be in a superposition of all 2 to the power n states simultaneously. That's exponential parallelism. But again, it's not that the computer is trying all answers at once and picking the best, because when you measure, you only get one result. The power comes from interference. You design operations so that paths leading to wrong answers cancel and paths to right answers add up. Shor's algorithm for factoring large numbers does this with the quantum Fourier transform. It turns the problem of finding the period of a function into a superposition where wrong periods destructively interfere. This could break current encryption, hence the race for quantum-safe cryptography. Grover's algorithm searches an unsorted database quadratically faster. Classically, for n items, you need about n over 2 guesses on average. Quantumly, you need about the square root of n again, via interference amplification. Then there's quantum sensing. Superpositions are exquisitely sensitive to disturbances. A particle in superposition of 2 paths acts like an interferometer. If something, like a gravitational wave or a magnetic field, changes the length of one path, the interference shifts. That's how LIGO detects spacetime ripples, laser light in superposition of 2 long arms. A passing wave changes the arm lengths by less than a proton's width, and the interference pattern moves. Atomic magnetometers use superposition of electron spins. A magnetic field makes the spins precess at different rates, changing the interference when you recombine them. These can detect brain signals, magnetoencephalography, without surgery. Even photosynthesis may use quantum effects. In plant light harvesting complexes, energy from sunlight travels as a superposition over multiple molecular paths, finding the most efficient route to the reaction center. It's like the energy explores all paths at once and picks the fastest, via quantum coherence. So superposition isn't just lab curiosity. It's in nature, and we're learning to harness it. Let's recap what we've covered so far. First, classical physics fails at small scales: energy quantization, wave-particle duality. Second, particles have wave-like behavior, de Broglie wavelength, electron diffraction. Third, the wave function describes the quantum state. Its square gives probability. Fourth, superposition means multiple possibilities coexist and interfere. Fifth, the double-slit experiment proves it. Interference vanishes when you measure the path. Sixth, measurement causes apparent collapse, but interpretations differ. Copenhagen versus many worlds. Seventh, decoherence explains why big things look classical. Environmental entanglement destroys interference. Eighth, superposition applies to all properties: position, spin, energy, not just location. Ninth, entanglement and Bell's theorem show quantum correlations can't be explained classically. 10th, applications, from computers to sensors to biology, rely on maintaining and manipulating superposition. In all of this, one idea recurs. Information isn't just about the system, it's part of the system. The act of knowing, or the potential to know, changes the behavior. That's deeply different from classical intuition. But here's the beautiful thing. Once you accept that the quantum state is primary, and that it evolves deterministically until measurement, everything follows. Schrödinger's equation tells you how the wave function changes with time. It's a differential equation, relating the rate of change of the wave function to its curvature in space and the potential energy landscape it's in. In words, the rate of change of the quantum state wave with respect to time is proportional to the negative of Planck's constant divided by 2 pi, multiplied by the sum of the second spatial derivative of the wave function and the potential energy times the wave function, all divided by twice the mass. That's the time-dependent Schrödinger equation, spoken fully. Solutions to this equation for simple cases, like a particle in a box or a harmonic oscillator, give standing waves. Discrete energy levels emerge naturally. No arbitrary assumptions, just wave mechanics in confined spaces. For the particle in a box, imagine an electron trapped between 2 walls it can't penetrate. The wave function must be 0 at the walls, like a guitar string fixed at both ends. Only certain wavelengths fit: half a wave, 1.5, etc. Each corresponds to a specific energy. In words, the allowed energy levels equal the square of the quantum number times Planck's constant squared, divided by 8 times the mass times the square of the box length. The ground state, the lowest energy, isn't 0. There's always motion, 0-point energy, because if the particle were perfectly still, you'd know its position and momentum exactly, violating the uncertainty principle, which says, the product of the uncertainty in position and the uncertainty in momentum must be greater than or equal to Planck's constant divided by 4 pi. Uncertainty isn't about measurement error, it's about the wave nature. A sharply peaked wave, small position uncertainty, must be made of many wavelengths, large momentum uncertainty. A single wavelength, definite momentum, is infinitely spread out, total position uncertainty. Superposition is baked in. And finally, why learn physics while you sleep? Because these ideas aren't meant to be crammed. They're meant to settle, to percolate. Your brain consolidates memories during sleep. Hearing the logic slowly, repeatedly, lets the patterns sink in. You don't need to solve equations, you need to recognize the structure. Quantum superposition seems bizarre because evolution didn't prepare us for it. We're adapted to medium-sized objects at medium speeds, but the universe doesn't care about our intuitions. It runs on quantum rules, always has, always will. And the more we lean into the weirdness, the more powerful our understanding becomes. A particle in two places at once isn't magic. It's wave mechanics, it's interference, it's information. And once you see it not as a paradox but as a feature, you start to glimpse the deeper layer of reality. One where possibilities dance together, where observation shapes outcomes, where the universe is not a collection of things, but a web of relationships. That's the world quantum mechanics reveals, and we've only just begun. Let's now turn to one of the most famous thought experiments in all of physics, Schrödinger's cat. In 1935, Erwin Schrödinger proposed it, not as a serious suggestion, but as a reductio ad absurdum, to show how bizarre the standard interpretation of quantum mechanics seemed when scaled up to everyday objects. He imagined a sealed box containing a cat, a tiny bit of radioactive material, a Geiger counter, a hammer, and a vial of poison. The radioactive material has a 50% chance of decaying in 1 hour. If it decays, the Geiger counter detects it, triggers the hammer, breaks the vial, and kills the cat. If not, the cat lives. Now, according to quantum rules, the radioactive atom is in a superposition of decayed and not decayed until it's observed. And since the fate of the cat is tied directly to the state of the atom, the entire system, atom, Geiger counter, hammer, poison, cat, must also be in a superposition. So before we open the box, the cat is neither alive nor dead, but in a superposition of both. Schrödinger found this ridiculous. A cat can't be both alive and dead, and he was right in practice. But the point wasn't to claim cats are in superpositions. It was to highlight the measurement problem. Where does the quantum world end and the classical world begin? When does the wave function collapse? When the atom decays? When the Geiger counter clicks? When the cat breathes or does? When the human looks? For decades, this was philosophy. But in the last 30 years, we've built real cat states. Not with actual cats, of course, but with systems large enough to blur the line. A cat state in quantum physics means a superposition of two macroscopically distinct states, like a current flowing clockwise and counterclockwise at the same time in a superconducting loop. In 2000, a team at Stony Brook University created such a state using a superconducting quantum interference device, a SQUID. They cooled it near absolute zero and used magnetic fields to put 1 billion electrons into a collective superposition, all moving one way and all moving the other way simultaneously. The two states differed by a measurable magnetic flux, macroscopically distinguishable, and they saw interference between them, proof the superposition was real. More recently, in 2020, researchers at ETH Zurich placed a tiny glass bead, about the width of a human hair, into a superposition of two vibrational states using laser light in an optical cavity. The bead contained trillions of atoms. Still, under extreme isolation, quantum behavior persisted. So Schrödinger's cat isn't science fiction anymore. It's an engineering challenge, and we're getting better at it. The barrier isn't size per se, it's isolation from the environment. Keep the system cold, dark, and quiet, and coherence. The maintenance of superposition can scale up further than we once thought possible. But here's a subtle point. In these cat states, the superposition is engineered. We don't just wait for a random decay. We carefully prepare the state using precise control pulses. That's key. Superposition isn't passive, it's active. It requires preparation, protection, and timing. Which brings us to time itself and how superposition evolves. Recall Schrödinger's equation. It tells us how the quantum state changes smoothly and deterministically over time, as long as no measurement happens. This evolution is called unitary evolution. It preserves probabilities. It's reversible in principle. If you could reverse all the momenta in the universe, the wave function would unwind back to its earlier form. In contrast, measurement is irreversible. Once you see the cat is alive, you can't unsee it. The information leaks into the environment, and with it, the possibility of interference. But what if you delay the choice of whether to measure? That's the idea behind the delayed choice experiment, proposed by John Wheeler in the 1970s and later realized in the lab. Imagine a cosmic scale double slit. Light from a distant quasar bends around a galaxy, gravitational lensing, creating two paths to Earth, like two slits. We can choose to detect which path the photon took, or let the paths recombine and look for interference. Wheeler asked, what if we wait until after the photon has passed the galaxy, billions of years ago, to decide how to measure it? Does the photon decide back then whether it was a particle or a wave, based on what we'll later choose to do? Experiments with lab-scale versions, using fast optical switches, confirm, yes. If you insert a beam splitter at the last moment to recombine the paths, you get interference, even though the photon had already committed to a path long before. If you leave the paths separate, you get which path information and no interference. This suggests that quantum events aren't fixed until they're registered in a permanent record. Reality isn't a sequence of definite states. It's a network of correlations that only crystallize when information becomes irreversible, like a photon hitting a photographic plate or a neuron firing in your brain. In other words, the past isn't written until the present asks a question about it, not in a mystical sense, but in the rigorous sense of quantum information theory. The history of a system depends on how you interrogate it now. That leads us to quantum contextuality, a deeper layer revealed by the Kachen-Specker theorem in 1967. It says, you cannot assign definite values to all possible properties of a quantum system in a way that's consistent with the predictions of quantum mechanics. For example, consider a particle with spin. Spin isn't like a spinning top. It's an intrinsic form of angular momentum with only certain measurable directions. For a spin-1 particle, if you measure spin along the x-axis, you might get +1, 0, or -1. Same for y or z. Classically, you'd assume the particle has definite values for all three, even if you only measure one. But Kachen and Specker prove that no such assignment is possible without contradiction. If you demand that the values obey the same algebraic relationships as the quantum operators. Experiments with trapped ions and photons have confirmed contextuality. The outcome of measuring spin in direction depends on whether you measure it alongside B or alongside C. Even if B and C commute with A, the value isn't pre-existing. It's created by the context of the measurement. Superposition is the engine of this. When a system is in superposition, its properties aren't merely unknown, they're indeterminate, not hidden, not waiting to be revealed, actively undefined until a specific question is asked. Think of it like this. A musical chord isn't just a list of notes played at the same time. It's a new entity with harmonics, beats, timbre, that doesn't exist in any single note. Similarly, a quantum superposition isn't just A or B, it's a new state C, with its own behavior, its own evolution, its own potentialities. And this is why quantum mechanics resists visualization. You can't draw a little ball in two places. You need abstract state space, Hilbert space, where each possible configuration is a direction and superposition is a vector pointing in between. The length of the vector gives probability, the angle gives phase, which controls interference. Phase is everything. Two states with the same probabilities but different phases behave completely differently. Add them one way, constructive interference. Add them another, destructive. That's why quantum gates in a computer aren't just probabilistic switches, they're phase rotators. For example, the Hadamard gate. A fundamental operation takes a qubit from state 0 and puts it into an equal superposition of 0 and 1 with a specific phase relationship. In words, after the Hadamard operation, the coefficient for state 0 is 1 over the square root of 2, and the coefficient for state 1 is also 1 over the square root of 2. Then, if you apply Hadamard again, the phases cause the 1 parts to cancel and the 0 parts to reinforce, returning you to state 0. It's like a quantum echo. That would be impossible classically. A 50-50 random switch applied twice would leave you random, not back where you started. But quantum interference makes it deterministic. Now, let's talk about how we know superposition is real, not just a calculational trick. Because over the last 20 years, physicists have closed the major loopholes in tests of quantum foundations. The big three are the locality loophole, the detection loophole, and the freedom of choice loophole. The locality loophole asks, could the particles be secretly signaling to each other after they separate, faster than light, to coordinate their answers? To close it, you need measurements so fast and so far apart that not even light could carry a signal between them in time. In 2015, 3 independent experiments by groups in Delft, NIST, and Vienna did this using entangled electrons in diamonds or entangled photons over distances exceeding 1 kilometer. They saw violations of Bell's inequality, ruling out local hidden variables. The detection loophole asks, what if your detectors miss most particles and the ones you do see are a biased sample? To close it, you need detection efficiency above about 80%. In 2016, a team in Munich used entangled atoms in traps, nearly 100% detection, and confirmed the violation. The freedom of choice loophole asks, what if the settings of your measurement devices aren't truly random? What if some hidden variable influenced both the particle source and your choice of angle billions of years ago? To close this, in 2018, the cosmic Bell test used light from distant quasars, emitted 7 billion years ago to determine the measurement settings. The idea, if any hidden variable set the particles, behavior, and the quasar light, it would have had to do so before Earth formed. Yet Bell's inequality was still violated. In 2022, the Nobel Prize in Physics was awarded to Elaine Aspect, John Clauser, and Anton Zeilinger for their pioneering work on entangled photons and Bell tests, confirming that quantum mechanics is not just correct, but inherently non-local and indeterminate. Superposition isn't optional. It's how nature works. So where does this leave us? With a universe that is, at its core, participatory. Not in the sense that consciousness creates reality, but in the sense that interaction defines reality. Properties don't exist in isolation. They emerge from relationships. This is echoed in quantum field theory, the framework that combines quantum mechanics and special relativity. There, particles aren't the fundamental entities. Fields are. The electron field, the photon field, the quark field permeate all of spacetime. What we call a particle is a localized excitation, a ripple in that field. And even the vacuum, the empty space, isn't empty. Due to the uncertainty principle, fields constantly fluctuate. Virtual particle-antiparticle pairs pop in and out of existence, borrowing energy for fleeting moments. These vacuum fluctuations have real effects. They shift atomic energy levels, the Lamb shift, and cause spontaneous emission. They're why atoms don't stay excited forever. In fact, spontaneous emission is itself a superposition phenomenon. An excited atom is coupled to the electromagnetic field vacuum. The combined system, atom plus field, is in a superposition of atom excited, no photon, and atom ground, 1 photon. Over time, the amplitude flows from the first to the second, like water draining from one tank to another. The decay is exponential because it's a continuous leakage of probability amplitude into the photon modes. In words, The probability that the atom remains excited decreases exponentially with time, with a rate equal to the square of the transition dipole moment times the cube of the transition frequency, divided by 3 times pi times the speed of light cubed times Planck's constant cubed. That formula, Fermi's golden rule, shows how superposition and coupling to a continuum of states produce irreversible decay. Even without an external photon, the vacuum provides the pathways for interference and transition. Now let's bring this home to something tangible: quantum teleportation. Despite the name, it doesn't move matter faster than light. It transfers quantum information, the exact state of a qubit, from one location to another, using entanglement and classical communication. Here, how it works. Alice has a qubit in an unknown state, say, alpha times 0 plus beta times 1. She also shares an entangled pair with Bob, one qubit with her, one with him, the Bell state where both are 0 or both are 1, with equal amplitude. Alice performs a joint measurement on her 2 qubits, the unknown one and her half of the entangled pair. This measurement has 4 possible outcomes, each with 25% probability. Crucially, this measurement entangles the unknown state with Bob's qubit, even though they've never interacted. But Bob's qubit is now in a state that's related to the original, just transformed by a simple operation, maybe flipped, maybe phase shifted, maybe both. Alice sends the 2-bit classical result of her measurement to Bob, say, via radio. That takes time, at most light speed. Bob then applies the correct correction based on Alice's message, and his qubit becomes an exact copy of the original. The original is destroyed in the process, thanks to the no-cloning theorem, which says you can't copy an unknown quantum state. Teleportation moves it, not duplicates it. The key resource is entanglement, a form of superposition shared across space. Without it, you couldn't do it. And without the classical message, Bob wouldn't know which correction to apply, so no faster-than-light signaling. This has been demonstrated over distances exceeding 1,000 kilometers via satellite. In 2017, the Chinese satellite MISSIS teleported photon states from ground to orbit. It's a cornerstone of the future quantum internet, where superposition and entanglement connect nodes in a fundamentally secure network. Because here, another application, quantum key distribution like the BB84 protocol. Alice sends Bob a stream of qubits, each prepared randomly in one of 2 bases, say vertical, horizontal, or diagonal. Bob measures each in a randomly chosen basis. Later, they publicly compare which bases they used, keeping only the cases where they matched. Those bits form a secret key. Why is it secure? Because any eavesdropper, Eve, has to measure the qubits to read them, but measuring in the wrong basis disturbs the state, thanks to superposition. If Eve guesses wrong 50% of the time, she introduces errors. Alice and Bob can detect those by checking a subset of their bits. If error rate is too high, abort the key. In words, the probability that Eve introduces a detectable error on a given qubit is 25%, because half the time she picks the wrong basis, and half of those times her measurement changes the state in a way Bob can spot. This isn't theoretical. Commercial systems exist, used by banks and governments. The security doesn't rely on computational hardness, like factoring large numbers. It relies on the laws of physics. As long as quantum mechanics holds, the key is unbreakable. Now let's address a common question. If particles can be in 2 places at once, why can't we? Why don't you experience superposition? The answer lies in scale and in the nature of perception. Your body contains about 10 to the 27 particles. Each is constantly interacting with air, with light, with itself. Decoherence time for a human-scale object is something like 10 to the minus 20 seconds, far shorter than any neural process. so any superposition would vanish before a single neuron could fire. But more deeply, you are not a single quantum system. You're a thermodynamically open, highly dissipative classical information processing system. Your memories, your sense of self, they rely on irreversible processes, ion channels opening, neurotransmitters binding, heat dissipating. These processes continuously measure the world, collapsing superpositions into definite records. Consciousness likely emerges from this classical stability. A brain in quantum superposition wouldn't have a coherent stream of experience. It would be fragmented, inconsistent. Evolution favored robustness over quantum weirdness. That doesn't mean quantum effects play no role in biology. As mentioned earlier, evidence suggests photosynthetic complexes use coherent superpositions to transport energy with near-perfect efficiency. Bird navigation may exploit entangled electron pairs in cryptochrome proteins, sensitive to Earth's magnetic field via quantum interference. Even our sense of smell might involve quantum tunneling in odorant receptors. But these are highly specialized, protected processes, occurring in cold, structured environments inside cells, not whole organisms in superposition. So the takeaway isn't that quantum mechanics doesn't apply to large things, it does. It's that for large, warm, wet systems, the quantum behavior averages out to classical behavior so fast that it's invisible. Like how a movie looks continuous, even though it's 24 still frames per second. The underlying grain is there, but smoothed over by scale. Let's now talk about time in superposition, a cutting-edge frontier. Just as particles can be in superposition of locations, can time itself be indefinite. In 2020, a team in Brisbane proposed and simulated a quantum switch, where the order of two operations is in superposition. Operation A before B and B before A happen at the same time. This isn't just theoretical. In 2018, photonic experiments demonstrated it. They sent a photon through two operations, say, polarization rotations, in a superposition of orders. The final state couldn't be explained by any probabilistic mixture of fixed orders. Only a genuine superposition of causal orders worked. This challenges our deepest assumption, that events happen in a fixed sequence. In quantum gravity theories, like loop quantum gravity or string theory, spacetime itself may be emergent from more fundamental quantum entities. If so, superposition of geometries, of distances, durations, even topologies, might be possible. A black hole's interior, for example, may exist in superposition with its Hawking radiation, resolving the information paradox. Or the Big Bang may not have been a single event, but a quantum transition from a prior state, perhaps a big bounce from a previous universe. We don't have experimental access to those regimes yet, but tabletop experiments with quantum simulators, using cold atoms or trapped ions to mimic gravitational systems, are beginning to probe these ideas. Which brings us back to the original question: why can quantum particles be in two places at once? The short answer: because they're not particles, not in the classical sense. They're excitations of quantum fields, and fields don't live at points. They live everywhere with amplitudes that can add and cancel. The deeper answer: because the universe is not made of stuff, it's made of potential, of possibilities held in tension, of relationships that become definite only when probed. Superposition is the mathematical expression of that openness. It's not a bug, it's a feature. It's what allows atoms to bond, light to interfere, stars to shine, and life to evolve. Without superposition, the periodic table collapses, chemistry vanishes. The world becomes static, inert, dead. So next time you see a rainbow, remember, those colors exist because sunlight, a quantum superposition of all frequencies, was separated by a prism, and each frequency interfered constructively at a different angle. Next time you use GPS, remember, it works because atomic clocks, relying on superposition of energy states, tick with such precision that we can triangulate your position to within meters, correcting for both special and general relativistic time dilation. Next time you take a photo, remember, the CCD sensor in your phone detects photons whose arrival probabilities were shaped by quantum interference in the lens and aperture. You are living inside a quantum world. You always have been. The weirdness isn't out there, it's in here. In the silicon of your devices, in the chemistry of your cells, in the light from the stars. And the more we learn